Thanks for asking.
So an update on your exam. I haven't actually graded them yet. So I still have another class I have to get through. I will hopefully have them graded this weekend sometime. I don't know if that'll be Saturday or Sunday, but I'll post an announcement here that your grades have been posted on D2L. All right. The other thing, just if you're unfamiliar, I will post our exam keys here and blank exams here on D2L. So the key is up. You can check if you're anxious about what you did. You might could look at the key if you can remember. I'm sure certain problems stuck with you more than others, but and you can print off the blank exams if you want to just take those as practice. A lot of people like to do those before, especially as we get closer to the final. So those are there for you as well. Did y'all have any questions or comments about the exam or on the exam? So what we're doing in Chapter 8 is Chapter 8 is giving us more integration techniques other than just a U substitution. So that's everything in Chapter 8 except for the last section in Chapter 8 has to deal with a new technique that'll help us integrate different types of functions. So here's some basic integration formulas that you should remember these. The inverse secant antiderivative number 13, not quite as common, but the inverse sine and the inverse tangent 11 and 12, those are very common. So you should definitely know those. And I would get familiar with these as they are, as opposed to having to do U substitution to figure these out, just because it'll end up saving you a lot of time. And so in 8.1 it says basic approaches to integration. Really in 8.1 we don't learn any new techniques. It's algebraic techniques to help us integrate. Some we've probably seen before, other techniques we probably haven't seen in a long time. So just as a reminder, the chain rule for derivatives is directly related to U substitution for antiderivatives. So if we notice there's a chain rule present in the antiderivative, then that's when our U substitution comes in. So just in general, when we take the derivative of a function that's composed with another function, U of x, we have to take the derivative of the outer function and leave the inside function alone, and then we multiply by the derivative of the inner function. So, reversing that process, we've seen many times, like an integral such as the antiderivative of x squared times the square root of x cubed plus 1, up to a constant, of course, but that's our inner function here. This is our U of x, and that's our U prime. So that's kind of why, I guess we could say that's f of U, and then that's U prime. So that's, in practice, we see those U substitutions coming into play when we notice an inside function's derivative is sitting out inside the integrand as well. Okay. So when we take the derivative of like sine of 5x, we say the derivative of sine is cosine, but we leave the inside alone, and then we multiply by the derivative of the inside. And so when we look at, look at formula number 3 above. You see the antiderivative of cosine of ax. We have that 1 over sine of ax. It's because reversing the chain rule here involves not multiplying through by 5, but dividing through by 5. So we have that, that inverse relationship between derivatives and antiderivatives. I think that the better you are acquainted with that, the more efficient doing these integrals will be. Is all of this blank? Oops. Okay, let me reopen that. Because it didn't like the other pages. Let's just make sure that they're, yeah, it's. Alright, I'm just gonna trash that.
Was it like how you typed it in English? Just like the audio? I had like the first time I did it, there was like 2 buttons there. I was like, just typing it in.
Sorry about that. I don't know why that was. All those other pages were deleted.
What's going to be the last section that we go over for the next exam?
For Unit 2,
Yeah.
it's 8.9, I believe, or 8.7. Okay, for Chapter 8, it's 8.9, but then we also look at 9.1 and 9.3. So then when we say, use substitution, hopefully you're at a point where you don't have to use substitute for this thing. Let's say the antiderivative of sine is what? Negative cosine of 5x. And then, the derivative we multiply by 5, the antiderivative we divide by 5. So that's kind of I guess technically it's a use substitution, but hopefully we're a little more efficient than that. All right. So the use substitution undoes the chain rule. The next section in 8.2, we look at how do we undo the product rule. And I do want to come back to this first example. So we'll come back to that first example. So again, no new techniques are presented in 8.1 for integrating. So it says use trig identities to create a function that's possible to integrate. So it's sine cubed over cosine to the 5th. So I don't know, identities is, I don't know. When I hear identities, it invokes fear because I'm like, there's millions of identities, right? To me, that's not helpful. But a lot of it is tying back to what do I know how to integrate, especially in 8.1 where we don't have other techniques besides use substitution. So let's think of an appropriate way to break down sine cubed over cosine to the 5th so that we can integrate it. Any suggestions? Yeah.
Break it down into sine cubed over cosine cubed.
So if we write this as sine cubed over cosine cubed
Times 1 over cosine.
times 1 over, oops, that's getting crooked, cosine squared. I mean, initially it doesn't look helpful, but let's rewrite sine cubed, cosine cubed as tangent cubed. And 1 over cosine squared is secant squared. Okay, so is that helpful? So why would that be a helpful way to do that? What can we do with tangent cubed secant squared?
Substitute tangent for u.
Yeah. So this is now a use substitution because hopefully we recognize secant squared as the derivative of tangent. So if I let u equal to tangent, then my du is the rest of that. secant squared x dx. So this is another type of integral powers of trig functions that we see in 8.3. So 8.3, we sort of revisit the idea of like how would we integrate like sine squared times cosine squared and those kinds of things. And when we do get to 8.3, what you see is there's certain techniques involved, but they're all u substitutions. So even in 8.3, we're still relying on a u substitution. Okay, so that's helpful in the sense that this becomes u cubed du. Which is u to the 4th over 4 plus our constant. Resubstitute, we have tangent to the 4th over 4. As the antiderivative.
I feel like this section before the test we just had, at least.
What?
I feel like the section that we're going over right now before the last test was really useful.
Oh yeah. Maybe, I don't know. I don't think I had any integrals on our first exam where you had to do like really fancy stuff. But yeah, maybe just to like solidify that. Yeah. Okay. So a lot of it, just like with algebra, it's not obvious. Like what should I do here? It may not be obvious to you at first. The point is just get a couple of techniques down so that we have a tool belt essentially. And then when we look at something, we can say, well, this didn't work, let me reconfigure and try something else. That's super common when you're finding the antiderivative. It's not something that you can expect to come to you immediately, right? The more you work with them, the more kind of patterns you develop. And then you say, oh yeah, here is where I would use a technique XYZ versus U substitution. So it's just a matter of exposure.
On a test, if we didn't put plus C, would you mark us down?
I feel like we've covered that before. If you don't put plus C, yeah, it's not. I mean, it's a technical oversight on your part, but I don't think it warrants points being taken off. It certainly becomes more prevalent in chapter 9 when we start looking at differential equations. So when you start looking at differential equations, the constants do matter, and if you forget them, then your solutions are going to be screwed up. So it is something you should be mindful of, but I don't, as far as antiderivatives, I don't know that warrants me taking points off. Okay. So example 3, I'm sure you've seen instances of this in Calc 1 where you have, a bunch of things added or subtracted on top and you've got a single thing on the bottom. The strategy there was to just split those up into 2 different fractions and simplify if you can. So that's an approach we can take here. We can say that's 4 over e to the 3x plus e to the negative 2x over e to the 3x. So splitting that up then allows us to look at it as 4 times e to the negative 3x plus e to the negative 5x. So just a small algebraic simplification gives us something that we can integrate here. Maybe a u substitution, but again, hopefully you don't need that. So what is the antiderivative of 4e to the negative 3x?
4e to the negative 3x, so we're at negative 3.
Right, so we're going to divide through by the negative 3. So we have negative 4/3 e to the negative 3x. And then the antiderivative of e to the negative 5x, similar thing. We have e to the negative 5x divided by negative 5. And that's it. there's another common technique here that we could utilize. So does anyone see another way to get where we got? Something we can do besides splitting it up? It's kind of it's algebraically equivalent, as we'll see, but it is also another technique to multiply your integrand or your function here by a form of 1. That's more conducive to simplifying it more or less. So let's rewrite this here. Or our second approach, we could say that we've got, what was it? I don't remember what it was. 4e. Okay, so it's 4 plus e to the negative 2x over e to the 3x. So if we multiply our integrand by e to the negative 3x over e to the negative 3x, so just multiplying through by 1, then that causes our denominator to be 1. And we have 4 times the e to the negative 3x plus e to the negative 5x. Just absorb that here. So you get the very same thing we just integrated. So either of those, any questions on that? I do want to take an aside. It's directly related to what we're doing, but through this other pattern that if we notice, it'll save us a lot of time in integrating certain things. That has to do with the natural log function. So the more general case, the natural log of f of x. What is the derivative of the natural log of some function of x? 1 over the function times the derivative of the function, right? So it's f prime of x over f of x. All right, so knowing that and looking at that in reverse, the antiderivative of f prime of x over f of x is, and remember this was in a more general setting, the derivative of the natural log and the derivative of the natural log of the absolute value were the same thing. Okay. So we'll remember that if we have the antiderivative of f prime over f, then that's just going to be the natural log, the absolute value of f of x. So this is very, I think, a very efficient thing to remember. Because again, it's not that we couldn't get there with f prime over f, that's a u substitution. It's not that we couldn't get there, it's just there's a lot more steps involved than just recognizing that is the natural log of the absolute value. So if you just want to keep doing u substitutions on those things, that's totally fine. So a couple of examples of where this comes in. Example 1, let's look at well, yeah, we'll do this one first. So the antiderivative of x over x squared plus 1. So the thing we recognize hopefully as a u substitution, because the function on the bottom has it up to a constant, its derivative is up on top, right? So when we look at this through the lens of a u substitution, we say, well, u is equal to 2x, and then we put that 2 on the other side with the du and say 1/2 du, right? So thinking about, well, this function on the bottom, its derivative is 2x. Wouldn't it be a lot more straightforward if that were 2x right there instead of 1x?
Yes.
Okay, well, can we make that 2x? I mean, we can make that a 2x only if we do what else to the integrand?
1/2.
Yeah, put a 1/2 on the outside or next to this. So if I multiply this by 1/2 and by 2, then I have this perfect relationship between function and its derivative, right? If that doesn't make sense, then maybe go through this in a u substitution, and you see that 1/2 gets inserted in there. So I'm going to put that 1/2 out here. And now we recognize that this is a function, and above is its derivative. So that's now in that logarithmic form. So if that's recognizable, then we can immediately say that that's natural log absolute value of x plus 1. We had that additional 1/2 in there, plus our constant. So I think either way, you're going to have to recognize either that's a u substitution and go through the process to get 1/2 natural log, or you can just recognize it as this sort of logarithmic form already. It's really up to you. And then actually here, we would say that it's just 1/2 ln x squared plus 1. So since the x squared plus 1 is always positive, we don't need the absolute value there. All right, another example where we kind of have a similar approach is if we had to find the antiderivative of tangent. So if we look at tangent as sine over cosine, remember the pattern this fits. It's the derivative is on the top, the function's on the bottom. So you might look at that and say, well, here's the function and here's the derivative on the bottom. The function over the derivative is not in logarithmic form. It's got to be the derivative over a function. Okay. And so here again we recognize, well, the derivative of cosine is minus sine. Wouldn't it be nice if that were minus sine right there? If it were, that's already in logarithmic form. But we're just multiplying this by -1, so we multiply this by -1, and we have the same thing, except for we've just kind of cleverly manipulated that so it is in logarithmic form. Okay. So then, what is the antiderivative of tangent?
Negative natural log of cosine.
Right, negative. So there's our negative from that -1. Natural log, absolute value, cosine x. So I guess that form is fine. Often you see this written as, so we'll say or, just the natural log of the absolute value of secant. So either one is the antiderivative of tangent.
That makes sense.
Do I see why?
Sure.
Not sure. Can you go over it?
So the -1 out in front of the logarithm can come up as a power on cosine. So it's cosine to the -1, and that's 1 over cosine, which is secant.
Thank you.
You're welcome. Cotangent, that's similar. We'll write that as cosine over sine. What's the antiderivative of cosine over sine? Yeah, it's just natural log absolute value of sine. Because again, function on the bottom, its derivative is on top. It's in log form.
Why was it that the absolute value wasn't necessary before Bernoulli?
So it depends on the function. Since this function, x squared plus 1, was always positive, we didn't need the absolute value. But initially it's there. Okay, I mean, we can look at an infinite variety of these, but I'll just put a couple more here. So the antiderivative of 9x squared minus 4x plus 1 divided by 3x cubed minus 2x squared plus x plus 4. What would the antiderivative of that be?
Natural log of denominator.
Yeah, natural log of our denominator, because the denominator's derivative is directly above. Whatever, and on we could go, but I think for efficiency, that if you utilize this, then utilize this. It's a lot more efficient. So maybe we'll just look at one more. 4e to the 2x plus 4x cubed all over 2e to the 2x plus x to the 4th. So function on the bottom, derivative is up top, and it's not even a constant multiple, right? It's kind of this one-for-one thing. Again, any one of these you can go through with u substitution and get the same result. If you want to verify it that way, feel free, but this is much more efficient if you can recognize. Does anyone have any questions on that? And in fact, the antiderivative for tangent and cotangent are brought up again in 8.3. So you should know those eventually. Okay. Another technique is when the integrand is an improper rational function. And it's improper if the degree of the numerator is larger than or equal to the degree of the denominator. So when you notice that, hey, the power in the numerator is larger than or equal to the power in the denominator, the approach is to break that down and make it simpler is to divide those things. So when this is the case, improper fractions, it's always going to be a long division process. So here, you could do synthetic division because you're dividing through by a linear. But remember, synthetic division was limited to dividing through by linear terms. If we go back to that first example, for instance, what we'll see is we're dividing through by a square. Synthetic division doesn't work for stuff like that. So I think it's definitely important to remember the process of polynomial division. So I guess let's take this off to the side. We have x squared plus 4 divided by x plus 6. And remember, the process involves us looking at sort of that leading term of the divisor, and then asking, well, what do I need to multiply this x by in order to get my x squared? So we're kind of comparing those two things. So if I multiply my x out front by an x, that's going to give me my x squared, and x times the 6 out front, giving me my 6x. So just like numerical division, you have to subtract that number. We have to subtract this polynomial. So once we find it, you have to subtract it. And so we have the x squared minus x squared, 0. We have 4 minus 0, and we have minus 6x. So we have our minus 6x and our positive 4. Since our divisor goes into this, we need to divide again. So we look at this x out here, and we say x times what gives me the negative 6x. So x times negative 6 gives me that negative 6x. And we start the process over. Negative 6 times x, negative 6 times the positive 6. And then we subtract off that polynomial. So we get 40. Divisor won't go into 40, so that's it. We're done with division. That's our remainder. So, do y'all remember how to express this now? So we would say that x squared plus 4 over x plus 6. Therefore, x squared plus 4 over x plus 6 is equal to what? X minus 6. And with our remainder, what do we do?
Plus 40 over x plus 6.
Yeah. Remainder over divisor. So that's our proper version of that function. Okay. So is that easy to integrate? The first two terms definitely are. What about the third term, the 40 over x minus 6?
It's going to be 40 over x plus 6.
Oh yeah, we divided by x plus 6. So. So the third term, use substitution, or we recognize the derivative of x plus 6 is 1, right? So that's just a log form. If you want to write it out as 3 different integrals, that's fine. Go ahead and do that. Okay. So the first term, antiderivative, x squared over 2 minus 6x. Here's our 40. And this 1 over x plus 6 is in log form, natural log absolute value of x plus 6. And that's it. That's our antiderivative. So sometimes the division, it will break it down into something easier, but sometimes after you've broken it down, you might have another simplification or a U substitution involved. So it doesn't fully take care of it for you always, but it does make it more manageable. Okay. Does anyone have any questions on that example? All right, with that in mind, let's go back to that first example. So why don't you all give that one a shot?
Yeah, that's where I got it.
Plus 2x to the 3.
Yeah, then you just got what? X squared over 2 plus.
Then you can use the basic order. Yeah.
And it seems like a bit.
Then you can use this basic.
Yeah, you just do your exponential.
Because of the unit. Cancel this out. Cancel another x to x to the negative 2, and then you'll have another x to the 2 x to the 2.
Because it is, yeah, by a form of 1. What'd you say?
It becomes a fraction. Oh, I get what you're saying. 2 to the negative 1 times 2 to the 2. Or 2 to the negative 1 times 2 equals 1. And you go to the 1.
So yeah, when you do the 1 plus 2.
Because x to the 1 times x to the 1.
Yeah, and then you also have a plus 2. Because x to the 1 times 5. Oh, you're talking about this one? Yeah.
This one or this one?
So you have 3 terms. So you need the ones like, instead of just 1 powers of x.
It's equivalent to.
Because doesn't x to the negative 2 and x to the 2 equal 1? That'd be multiplied, yeah.
That would just.
So it is plus.
On top of that, plus X.
You can't ask me to learn anything. I don't know math.
The other one that you were saying was
Squared plus 1. Then they cancel out there, and then you.
Then they cancel, but then you only have one term on the bottom.
No.
Yeah. You have one term on the bottom.
No, like the top and the bottom.
You know, I think maybe if you look
Yeah,
at
you
it
wouldn't do that.
initially, it might be a little more.
You would just let the bottom factor out.
Cancel, they're just making themselves stronger.
Then that gets rid of this, and I just have X over 1 plus.
Yeah, you know what, they probably would.
Sorry, X.
I thought it was
Two.
X squared.
Two times negative 1 times 2 to the 1.
Instead of multiplying
Can't do
by
that.
X,
Did you see what he just did?
it's
Or
multiplied
was he,
by.
it was the same.
Lowest common so.
Yeah, no, that doesn't work.
Yeah.
So then we have, then this becomes X cubed, this becomes X squared.
So how do you get 2x and negative 2?
Yeah. It's X to the negative 2 plus X squared.
So then that's where you have to default back to recognizing the power on the numerator
It doesn't
is larger than or equal
Like if you
to the
multiply it
power
by
on the
one.
bottom.
If you multiply
Now
by
it's-
X
now at
to
this
the
point,
1
we need to
plus
do
X
multiplication.
cubed over itself.
Yeah.
Did he just cube the whole thing? Or did he multiply by X? He multiplied by X to the negative 3. Or no, he multiplied by X to the
Lowest power?
Yeah, that makes sense. Because watch, when he does that, then you get X X squared plus. And then you just want this one like this one. And then you just pull out one. Yeah. And then you just pull out one round and multiply it so that it's
Over X cubed.
plus 1.
On the bottom, yeah, that'd be X squared.
Yeah, it's that thing.
So now you get X squared plus 1 goes into X cubed. I still don't know.
1.5. X.
You get a minus
X to the 1, right?
No.
Yeah. So you just multiply that.
negative X. How much is X? How many times is X cubed going to?
Plus X and subtract those, and you got negative X.
Yeah, how often is it?
I put the X plus 2 on.
When you multiply by.
Negative 1 over X? No.
Yeah. Wait, no, when you multiply by negative 3.
By X squared, how many times is X squared?
Just, okay, does x to the negative third?
It's X to the negative 3.
Because you just subtract.
Right? Yeah, it is. X to the negative 3. Because then it's actually addition. Or no, it's actually
So you write what's on the
subtraction.
bottom.
Which means that addition gives you X squared.
Like I just told you.
How many times does that go? Oh wait, that's a plus.
0x squared plus 0x plus 0, right?
1 to the negative 3.
Every power of x, right?
That's what I did.
Even if I don't have
Do you guys know how to do longer?
Yeah,
I know.
but I was like,
I did it in my pre-calc class.
wait, let me see. She's how you do it. Write out every power of x, like even if you don't have them, and that way you can like keep them straight in your brain. And then it's like figure it out.
I did it in pre-calc, and there was like a really long question, like a 4-term polynomial that you have to do it, and I got the whole question wrong because I literally wrote that 6 times 3 was 9. As the last part, when you give that, yeah.
So then you have to say, okay, what do I have to do this first term to get to this somehow? So we have to multiply this by to get to the
You have to multiply X squared by 1 over X.
Just multiply by
By
X.
negative 1 over X.
So you
So then you put x on top, right? And now you
So you have to say
actually do
negative 1
the
over X.
multiply x squared by
Just X squared times negative 1 over X.
1 minus.
I got 1
X,
plus.
and I'm gonna
No,
write that over
or 1
here.
minus 1
Under my like single power zone, and then just fill in the blanks.
So then you would multiply 1 by that.
1 over X.
Yeah.
Right, so then you parentheses that guy, yeah, and subtract.
And then you multiply it
Draw a
through.
bar, and now it's just subtraction straight down, so X.
And then multiply that. Right?
Yeah, then you get 0 and then you get minus 1 over X. That's your new term.
And then 0 plus negative 0.
And then you have to multiply this by negative X.
So then we have this now to get to
Like negative X.
Why is it this square?
Yeah, that's.
So,
So now you've got this right because x squared is larger.
you want the opposite.
So this one's a so there's your quotient. Yeah, that's fine. Quotient is just x. Yeah. And then remainder negative x
I'm usually the last person to finish a test. I went to a negative 1. I've never done that. You pull down that target, that target.
But that would be X with a negative 1 over.
X squared.
It's like 6 and then you go 1 to
Two plus
X. I think I'm not stuck, so like erase the power. And you go, that's gotta be wrong. No, I had to multiply that through.
So now you're saying, okay, so we're multiplying this by negative x to the negative. So when we do that, we get a negative x, right? Negative x to the
That's what I don't get those.
Now those cancel. And then you got no positive.
Subtract it. The x terms go away.
You go. Okay. What does x squared go to 1 over x?
We're like,
I think
Yeah, so you would start there.
But like, couldn't we
Because negative x, you can't
divide
divide negative x by x squared.
Does it ever end?
It's already proper.
My chem class here,
This is a lower degree than what we did.
I would like.
So what do I write?
Why, but multiplying it by negative 1 over X.
Then it becomes x minus x squared.
And then remainder negative x.
Yeah.
Whatever.
Yeah, that's your remainder. Oh, it is over. Yeah, that's your remainder. That negative x.
That's what I was doing for
I'm really glad I did a lot of it on this.
I mean, yeah, you were, how far is it?
Yeah, because it's not gonna, it's not gonna go into it in column either. Right?
Like what you're doing.
It's gonna be
Yeah, dude, part of the
negative
I'm
x.
actually like,
Yeah, we can multiply that by 1 over x, but now we're introducing negative powers of that, which we don't do like with all the
really, there's a picture something?
Yeah, because all of this turned into for this,
Oh my god, that's
right?
I created it.
And
Yeah, okay. So it's over x squared.
Oh, yeah, the 1 plus x squared. That was a x squared.
Okay.
Oh, and then you just get, and then you get the L and
Did you get x squared minus x to natural log x squared plus x squared? I got almost exactly 3 plus 1 x squared minus 1
Yeah,
over
right.
x squared and x.
Do we go over that?
no, I don't know if that's
I remember
explicitly mentioned.
I think it was, I think we did that. I pulled out a negative
Yeah, maybe we can go back to that last example. But that last example would be,
It was actually.
no, maybe not. I have to think about it.
Because you have to make this.
Oh,
yeah, that's right. That's how you just be like, okay, what's
So that's
that?
what-
She's looking at me. Actually,
Divided by
right?
seven.
X.
Let's see, I don't know, what would it be?
This is why you probably had to learn that. Like, well, now you have to really do it.
But now, like, you know, and also like what?
So remember, long division, you stop when the polynomial or your divisor is higher degree than your, what's left over here after your subtractions and stuff. So we stop there. Just like in that last example, we stopped when we got a 40, but we were dividing through by x to the first power. So this is 40x to the 0. We stopped there because that's x to the first and x to the 0. Here we're stopping because we're dividing through by x squared. Oops. And our result was an x to the first. So that's where we stop. Notice this derivative isn't quite there. That's a 2x. Then we have this negative 1/2 here. So now that's in logarithmic form. So we have x squared over 2 minus 1/2 ln x squared plus 1 plus c. But x squared plus 1, always positive. You don't need the absolute value there. So, however, it's fine as it is. It's just kind of redundant. I would. It's just redundant to write like that. I don't think there's anything inherently wrong with it. But I hope you can recognize when the absolute value is needed and when it's not. But yeah, it's probably not something I would be picky about. All right. So does anyone have any questions on that example? All right. One more technique. Completing the square. So looking at this one, it's not improper. We wouldn't go through long division to figure that out. But if we complete the square on the quadratic on the bottom, that might be helpful. So what does the completed square of x squared plus 4x plus 8 look like? Yeah.
Subtract 4 from the bottom, right?
Yeah. X plus 2 quantity squared plus 4. Or we take half of 4, square that, add it to both sides. So really what we're adding in here is a positive 4. Oops. A positive 4 to make that a perfect square. But if we add in 4, we also have to subtract in 4. So that's how we get the positive 4 on the outside. Yeah, it's probably been a while completing the square. Okay. The process is you take half of the b term and then we square that number to add to both sides. But we're not dealing with an equation, so if we add it in, we have to subtract it in. So we're just adding in 0 And then that way, that process completes the square on the variables, and then we have our positive 4 left. So yeah, does that help us?
Not really. Wait, you can't use sub.
Yeah, so it looks like we probably could in u sub, right? U substitution, we would say maybe let's let u equal x plus 2, but then the derivative is dx. How do we account for that x? Right? So let's look at it. Okay, so that we can account for this. The plus 4 is fine on the bottom. We account for the dx, but can we account for the x in the numerator with a u substitution? No? Who says no?
Substitute for you, but,
I say it works.
Isn't it true that if u is x plus 2, that u minus 2 is also x?
Yes.
So we can actually account for that x. The question is, if we do it this way and account for x that way, does that help? So I don't know. I don't know if this is going to help or not, but I'm going to write it out just to see. I'm exhausting my options at this point. So I've got a u minus 2 up top, and my du. The quantity x plus 2 squared, that's now u squared. Plus 4 stays plus 4. Doesn't look like much of an improvement, does it? Instead of one thing on top, now we have two things on top. Huh?
Fees.
Okay, you might try a v substitution, but you're going to end up kind of back where we are.
you can,
Yeah.
you can split it apart,
Okay.
and then you can use the f prime over f for the u over u squared,
Okay.
right?
Yeah.
And then the other one's just the ln, because it's just 2 over u squared plus 4.
Okay. Close. Very, very close. The idea is now what we couldn't do with the x over the x squared plus x plus 2 squared plus 4 is split that up. When we get these two terms in top, we can split this up now into two different integrals: u over u squared plus 4 du minus 2 times the integral of 1 over u squared plus 4. So the first one, as we've noted, is a u substitution, right? Function, derivative up top. So this is the same old thing we've done. If we have a 2 and a 1/2 there, now that's in logarithmic form. Okay. What about the second integral?
The inverse tangent.
Yeah, that one's the inverse tangent. Remember the one on your homework where it was 1 over y squared plus 16? It was the inverse tangent integral. This one here. We got 1 over u squared plus, what was it, 1? Or 4. So that a squared is 4, a is 4, right? Got to recognize that. Like I said, they're super common. And if you don't recognize like inverse tangent integral or inverse sine integral, then you're stuck. Like there's really nothing you can do, like u substitution. None of these techniques will get you the fact that this is inverse tangent. So a is 2 here. So we have 1/2 inverse tangent of u over 2. And then some constant. Any questions on that? Might have made some big leaps, I don't know. All right then. For which one? For the inverse tangent?
So you said there's no leeway to do that?
No. You guys, it's kind of like with the ln thing. You gotta just know that the antiderivative of 1 over x is
I know from the beginning.
from the beginning.
If you don't go to the u route,
From the x over x plus 2 squared plus 4. Maybe. Yeah, I don't have any alternatives off the top of my head. But yeah, there certainly could be one. Okay, we need to resubstitute as well. So you have 1/2 natural log. U was x plus 2, right? X plus 2. Yeah, x plus 2. So that's u squared plus 4 minus inverse tangent of x plus 2 over 2. Plus. So wait, can I get in there? Yeah, I don't know, you might be able to. Yeah.
So I added 2 to the top. Created a second one. By the top.
you probably can go then.
But from here,
You have x plus.
I have this.
This becomes the first part.
And then I make this the second part. So what I did, so I multiplied, I added a 2 to the top, and subtracted the 2, the same thing. And then I multiplied the top of 2 and so this part, so that just that's what you do. This is
So you take 1/2 of b squared, add it back, like you did last term, and then also subtract it from it.
So then at that point, you would complete the square thing, you would want to be in almost an identical place as we were with this negative 2.
Yes, what is it, negative 8?
Yeah, wait, there's
Got
something
four.
square would be something 2 over. No, our so then plus 4. And then that's 6
Yeah, that's u. That's 2, that's 1/2 tu.
So this term becomes irrelevant when you use that term to do the square thing, and then that's just a key.
Okay, and then
like this, like
I just would rather. That's what I.
Does anybody else have any other questions on that example? So that's pretty much A1. It's just sometimes obscure techniques. It's not often obvious. I hope what's obvious is sort of the log form is starting to get a little bit more used to that. And when you have to use long division, those should be pretty clear as to when to utilize those. But yeah, you know, the thing with derivatives is we had formulas for all derivatives, right? If I had a particular function and I said find the derivative, I say, oh well, that's a product and a chain rule. Okay. The problem with antiderivatives, as we'll see, is it's not as straightforward, right? Even though they more than likely came from a derivative, there are functions where you cannot find, there are some functions that have no known antiderivatives. So the process of taking a derivative, although easy, you were left wondering, hey, did I do that right? There's really no way to check that you did the derivative right. You just kind of hope that you applied the rules correctly. The process of finding antiderivative is much more difficult, but at least when you find the antiderivative, you can check your work, right? I check the derivative of my antiderivative should be what I ended up with in the integrand, or I might have to simplify it and tweak it a little bit, but it still, regardless, it should be the same thing. Okay. So this, this is a super common function, e to the negative x squared, or even e to the x squared. So, like e to the x squared, for instance, there is no known antiderivative. Yeah, if you put it in like Wolfram or something, it'll spit out this, this goofy function, e r f. It's this error function with stuff in it, right? But it's not, that's not really an explicit function as we know it to be. So, there's countless examples where functions don't have an antiderivative. So that's the nature of finding an antiderivative is a lot more difficult than finding derivatives. And it just takes exposure and practice to know like what situation am I dealing with. And sometimes it's just trial and error. Let me try this. Does it work? No. Let me try something else. Did that work? Okay. So that's it. There is no clear-cut method. I hope that as we go through chapter 8, certain patterns become really evident as to when to use them. But that's kind of the best we can hope for when we find an antiderivative. I don't mean that to be discouraging. I mean that to be sort of supportive. And when you're doing these problems, just have patience. It's not always clear cut. Okay. So if there aren't any other questions, I think we'll take a break and then start 8.2.
One of them was like a catapult angled 40 degrees above a wall and like the velocities.
All right, let's start 8.2. 8.2, we're going to look at integration by parts. And so integration by parts helps us undo a product rule. And we'll look at the function u of x and v of x and take its derivative. And there's the product rule for derivatives. And sort of how we can arrive at the formula for integration by parts is looking at the reverse of this, right? So let's see if I can fit this here. So I'm going to take the antiderivative of both sides with respect to x. I can't really fit that in, so I'll just write it out. I'm just going to write uv, and we'll just know that they're functions of x. Okay. So there's our product rule. We're going to take the antiderivative with respect to x. And so the left-hand side, the antiderivative and the derivative undo each other. So left-hand side is just uv. I'll split these two up here and write u prime. Remember that this is all with respect to x, so u prime is, we'll write as du over dx. So this is v times du over dx for u prime times our dx here plus the integral of u v prime, which is dv over dx times our dx. So the uv is equal to the dx's will divide out, so we have the integral of v times du plus the integral of u times dv. And it's sort of arbitrary, but universally accepted that we're going to solve for the integral of u dv. So we're going to subtract the integral of v du on both sides. Oops, what happened? Okay, that's weird. Okay. So this is our integration by parts formula. I know it doesn't look initially helpful, so I identify what we're actually working with. We're given this integral u dv. So that's the thing they give us to find the antiderivative of. And again, remember that dv is actually dv over dx times dx. So we have a function and a derivative here with u and dv. So given a particular product, u times dv, both of those will be functions of x. Again, this is, our differential is actually hidden here. So this is still a function of x. And u is a function of x. So we have two functions of x multiplied by each other with respect to x. So our task is to identify a u and a dv. And notice what else is present. If we have a u, present in the formula over here is the du. So we need the derivative of u. If we identify this other function as our dv, we have a v over here in the formula too, which means we need to find the antiderivative of dv to sort of put all of this together. So the process of finding the antiderivative using integration by parts involves identifying u and dv in the original integral, taking the derivative and the integral of both of our choices for u and dv, so we can fit it in as uv minus the integral of v du. Sometimes integration by parts is referred to as ultraviolet voodoo because you have the uv v du. I don't know if that's helpful to remember, but I've certainly heard it referred to that way by more than one person. Okay, so there's our steps. We identify u and dv, and we'll talk about the most appropriate choice for u and likewise dv. But we identify those two things in the original integral. We find du, which is the derivative of u, and v, which is the antiderivative of dv. And then we plug those into this formula on the left-hand side. The resulting integral that we get from this formula, the v du integral, should be easier or comparable to the original. If it's harder than what you started with, there's probably another technique that would be a lot easier to use. So v du integral should be easier or the same difficulty as the original function or integrand. So how to identify u and dv? Dv should be easy to integrate. The other way to think about this, I don't know if this is helpful or not, but I'm just going to mention it. This acronym actually stands for various types of functions. And with that acronym, if we can remember to let our u equal the leftmost letter or function in that acronym, then that'll give us a starting point on what u should be. When we know what u is, we know what dv should be. Okay. So these are, from left to right, are the harder to integrate versus the easier to integrate. So L are our logarithms. I, the inverse, mostly trig. A is algebraic functions. You know, like x squared, x plus 1 to the negative 2, square root of x cubed minus 1, those kinds of things. T would be for your trig functions, and E for exponential. So always let U equal the leftmost function in that particular setting, from logs to exponentials. So practice with e to the x cosine x dx. And the way we sort of start to recognize integration by parts is simply by the product, right? The formula is the integral of u dv. There's a product of two functions of x. There's a product of two functions of x. We should probably think, if it's not inherently obvious that's a u substitution, then product of two functions, we should default to integration by parts. So integration by parts always starts off where you identify the u and you identify dv. So that's always what you start off identifying. And so if we go by this mnemonic, I guess, we should let u equal the leftmost function in that acronym, which would be our trig function. Trig functions come before exponential. Okay. And then dv is the rest of that. dv is cosine x dx. These differentials with the d's should have differentials with them. We're not going to actually integrate that. I just wanted to get a couple of examples in with identifying u and dv.
Wait, what did this say?
Oh, yeah, sorry, that's e to the x dx. Thank you. I don't know why I wrote that twice. It's a long day.
That makes sense.
Okay. Okay, how about x squared sine x dx? What should our u be here? The algebraic part, the x squared. So our u should be x squared dv sine x dx. Another way to think about that is, if you want to think about it, it's sort of in reverse. dv should be the largest part of the integrand that you know how to integrate. That's the other way to think about it. All right, so we've kind of identified our u and our dv. Let's look at an actual example. To find the antiderivative of x times e to the x. So we're going to identify u and dv. So we should let u equal what? Our x, that's our algebraic. And then dv has to be the rest, e to the x dx. Okay. But the formula is uv minus the integral of v du. So not only do we need u and dv, we need du and we need v. So to get du, we're going to take the derivative of our substitution, u equals x, du equals dx. And to get v, we have to take the antiderivative of e to the x dx. Is everybody all right with that? So derivatives and antiderivatives are involved in finding an antiderivative. It's really easy to get wires crossed. Yeah, we'll put it in later. So let's say the integral of x e to the x dx is equal to u times v. So that's x times e to the x uv minus the integral of v du. Okay, the resulting antiderivative v du is easier than what we started with. We'll see an example later on in the section where the v du ends up being comparable or the same as what we started with, and we'll talk about how to handle those. Okay, so then that's actually pretty straightforward. X e to the x minus e to the x. All right. Any questions on that? Okay, so why don't you attempt number 2? You know, if time permits, you could check your work too, if you took the antiderivative correctly. This one is switched to this
Because I did it in the table, and I was like, these are not the same answers. Okay, yeah.
Just crazy key. Just like
Yeah.
They cross it. So, yeah, when
what time?
and
Crash party.
Yeah.
exactly. I just write it.
Costco, I'm going to take some to 11.
Yeah. Cool.
The crash party.
No, I
It's such a fun job because when I tell you,
Looks like everybody's done writing and checking Facebook or whatever. So, what did you come up with for the antiderivative of x cosine?
X cosine x minus sine x plus c.
Yeah, because like.
Okay, so x sine x,
No, x cosine x.
x cosine x minus
Sine x
sine x.
plus c.
Okay, what do y'all think? Did you come up with that?
I got some.
Got some different?
Yeah, I got x sine x plus cosine x plus
but
c.
why?
X sine x plus cosine x
I thought it was.
plus c.
Yeah.
Yeah.
Oh,
What was that first one?
Okay, yeah, we'll see what it is. So what are we gonna let u equal? The algebraic function? dv is then cosine x dx. du, derivative of x, is dx. Remember, we're just really taking the derivative of u with respect to x and moving that over on the other side. And the antiderivative of cosine yeah, the integral of cosine sine. So we have u times v, x times sine x, minus the integral of v du. And the antiderivative of minus sine is cosine. Anybody have any questions on that? So, you know, like there was a homework problem in 6.3 maybe, where it was find the volume, and the function they gave you initially was y equals to the inverse sine of like x over 2. And then you had to say, well, I don't know how to integrate that, so now I have to use with respect to y, right? So the integration by parts can also integrate inverse trig functions, if inverse trig functions are by themselves or with something else. So this is the technique that can find those antiderivatives for us. Okay, x, ln x, we have our algebraic times a logarithm. So our u should be equal to what? The log. Yeah, it's the furthest one on the left. So natural log x is u, and then that means dv has to be the x dx. Okay. Derivative of ln du is 1 over x dx. Antiderivative of x is x squared over 2. So again, it's just a product of two functions of x is usually a good candidate for integration by parts. So u times v, we've got 1/2 x squared ln x uv minus the integral of v du. So v times du, we have x squared over x, which is just x, times 1/2. Let me put that out here. Okay, so there's uv minus the integral of v du. Clearly, the new antiderivative is easier than what we started with, so this is probably going to work out. So we've got 1/2 x squared ln x. Antiderivative, we've got x squared over 2 times the 1/2 plus our constant.
So we don't know what the integral of the natural log is.
Yeah, right. We wouldn't want to choose dv to be ln of x dx because we don't know how to integrate natural log of x dx. Yeah, and one more example I believe we'll see that we can do. Well, a couple more examples. We'll see that we can do the antiderivative of the natural log with integration by parts. But for now, we don't know, so. Okay, questions on that example? So we can apply integration by parts more than once. And this, so if you apply it more than once, you've got the minus v du, integral of v du in your formula. So you just got to be careful with all your signs. The more you do integration by parts, the more of those negatives that you have to worry about reconciling. So we'll start off with this algebraic times a trig function. So we'll let u equal to x squared dv cosine x dx. du is then 2x dx. And v, the antiderivative of cosine. Cosine. All right, so integration by parts once. Let's see what that gives us. We have u times v. Minus the integral of v du. So that the new integral is pretty comparable to what we started with, right? It's still this algebraic times a trig function. So we've got to, in order to evaluate that second integral that emerges, we do integration by parts on that again. So I personally think it's bad form to use u again because we've already used u to equal x squared. So, I don't know, just for the sake of not confusing people, here u would be, again, our algebraic function, and dv our sine x dx. So du is 2 dx, and v, what would v be? Yeah, all right, just checking. Negative cosine x. All right, so this is kind of where we need to be careful because what we're doing is we're taking this integral here and we're about to split that up again into a uv minus the integral of v du, but both of them have this minus out in front. So just be careful with that when you do this more than once. So we have x squared sine x minus all of this stuff, uv minus 2x cosine x minus the integral of v du. would just recommend writing it out things explicitly and then dealing with the signs after the fact. If you do that in your head, that's fine. I think there's just a larger tendency to miss something that's positive, which should be negative, or vice versa. Okay. Everybody all right with where we are? Are there any questions? All right, so this is a minus integral of -2, so we can call that negative and that negative are now positive. And then if we want this to ungroup this sort of stuff, then we just distribute that negative into both of those. So it's x squared sine x minus 2x, so that's plus 2x cosine x minus the integral of 2 cosine x. And so that third integral there we can do. So what we have is x squared sine x plus 2x cosine x minus 2 sine x plus c. It's kind of a hassle to keep up with constants with a process like this. So just put it in at the end, because all of the other constants that emerge will be combined with the other constants to make one large constant. All right, any questions on that example? So be careful with your signs is the main thing here. There's another technique. I wouldn't call it another technique. I would call it a different way to compute these kinds of things. Some textbooks actually will mention explicitly in the section. Our textbook doesn't. Our textbook mentions it as kind of like this exercise towards the very end of the section. But I think it's very, very efficient for doing these kinds of things, especially if you have to do these over and over and over, like integrate by parts 4 different times. There's a more efficient technique to do that. So it's called tabular integration. It's still integration by parts, but it sort of takes all of the the tediousness out. So it's still integration by parts. So let's just stick with that last example to illustrate how this works. And maybe with a few more that we'll do by parts, and then we'll show, the tabular integration as well. Okay. So the identification of u and dv are still the same. We identify those the very same way. So we would say that, we're going to identify our u as x squared and our dv as cosine x dx. So we're going to make this 2-column table. All along the left-hand side, we're going to just look at derivatives. So the derivative of x squared is 2x, derivative of that is 2, and the derivative of that is 0. Antiderivative of cosine is sine. Antiderivative of sine is minus cosine, and then the antiderivative of that is minus sine. So here we're going to stop, just so when we stop with 0, because the way we piece this together matters. The other caveat here is when we do integration by parts, it's always minus the integral. But when we did this twice, we saw that then some of this minus thing turned into a plus, and that, so you've got signs to reconcile pretty easily here. The first row is always positive, then it's negative, then it's positive, then it's negative. So that's always across the row, starting with the top one, positive, negative, so on. And then we look crossways. So cross, we have x squared times sine x. Cross again, we have a minus 2x times minus cosine x.
The bottom one be a positive sine x, but
No.
The antiderivative of cosine is sine, but the antiderivative of negative cosine is negative sine.
oh, it's anti.
Yeah, derivatives on the left, antiderivatives on the right, yeah. Okay, so that was a minus 2x times minus cosine, and then we take our positive 2 times negative sine. That's it, this one's 0, we're not crossing that with anything, so that's the antiderivative right there, as we saw. You don't have to remember this way. I really don't care what you do to integrate by parts. It's really all the same. If you don't want to have to remember something else, don't remember it. Yeah.
So what if your first term wasn't something that would end in 0? You always just do it at 3 levels, or how do you decide how many levels?
It depends. Yeah, and we'll see an example where we have to, I don't know how to say it, but you basically end up with an integral that repeats. Yeah. So then we got to solve the equation for the integral. I don't think I actually put that. I'll put that in our notes just in case. I don't know that the textbook explains it any more clearly, but so I'll add a new page that's not in your notes and just take this from your textbook. So it's mentioned in exercise 77 and 8.2. Let me go back to that example. We can sort of break this out in stages. As long as we're crossing diagonally, then that's just a straight multiplication of those two functions. The other way we could interpret this is, to cross here and multiply these two functions. But if I go directly horizontal, then I have to integrate the product. So that would be the integral of negative 2x sine x. So if you go horizontally, it's still the product, but you have to take the integral of it. If we're just going diagonally, it's just the product. So if you'll notice, that was where, after our first round of integration by parts, that was what we ended up with. X squared sine x minus 2 times x integral sine x right here. Okay, so that's sort of what they explain through this example. So I'll leave that there if you want to reference that. We'll look at a couple more with integration by parts and with tabular integration, just so you can sort of get your bearings on either one. So this would be another candidate for tabular integration. Otherwise, we're going to have to do integration by parts twice. on this. So u is our algebraic, dv is our exponential, e to the negative x dx. Du is 2x dx. Excuse me. And what's v? Yeah, negative e to the negative x. Antiderivative of dv. All right, so we have u times v minus the integral of v du. So just, get in the habit of writing these out explicitly. Then if you can take care of negatives and negatives or whatever, do that. I think if you have to do this more than once, trying to combine things as you go, is probably detrimental at first. So this -2 and this right here will be a positive. Or you could just leave the -2x in there and integrate by parts with that. It doesn't matter. Once again, u is our algebraic, dv is our exponential. Du is 2dx. And v, again, negative e to the negative x. So we had that plus out in front of it, that integral, so it's just a straight thing here. And 2x times e to the negative e to the negative x minus 2x e to the negative x. There's u times v minus the integral of v du. It's minus 2 e to the minus x dx. So again, just plug in everything, then take care of the signs if you want. -2 in the negative integral here, that'll be a positive. And that one's easy to integrate. Okay, so antiderivative of e to the negative x again. It's going to be -2 e to the minus x. And since we're done with the integrals, we'll just put our constant in. That. You can see how much of a pain that would be, though, to check the derivative. Is the derivative of this x squared e to the negative x? I mean, it takes some time because you've got product rule, right? And you got to combine stuff. But you could do it in theory, time permitting. Okay. Is that all right? What we're doing? Anybody have any questions? Okay, so then we'll look at it using tabular integration. Tabular integration is integration by parts. So where integration by parts works, tabular integration works. A lot of times it's just knowing when to stop, because not all functions end in not all functions have an nth derivative that's 0. The identification starts out the same. Our u was x squared, and our dv was e to the negative x. Left column, we take derivatives. So again, that's 2x, 2, and 0. Remember to alternate their signs, positive, negative, and so forth. And then the right column, we find the antiderivatives. Then we cross top left corner diagonally. So that's going to give us our negative x squared e to the negative x. Diagonally again, it's a negative 2x times e to the negative x. And then diagonally once more, positive 2 negative e to the negative x. Same result, just efficient way to integrate by parts. All right, anyone have any questions on either of those?
What's the good situation where that doesn't work?
There's not a situation where it wouldn't work. You just gotta know when to stop sometimes.
Okay. So if you get to this repeating derivative, right?
Yeah.
So let's say it's like e to the x, for example. You know, it's not going to stop.
Yep.
So when would you have to just add going across, or you add the integral going across?
Yeah, so if we move horizontally, it's the product still, but it's the antiderivative of the product.
So it's the antiderivative of the product.
Yeah.
But you're still going to be left with, so you just have to figure out that last part.
Yeah, and we'll see an example here in a second. So we can solve these things too, right? Like if I start off with, I don't know, if I start off with this integral, and I say it's this a bunch of other stuff, and I end up with that, and I say, hey, well, if I keep integrating by parts, I can just go in circles because I keep getting the same integral. Well, all I have to do is add that integral to both sides, and then I have two of those, and then I'll divide by 2 to solve for that integral.
Oh, I got you.
Yeah.
So you're saying that you're probably going to end up with...
Well, either way, it works.
Either way it works, it's just you still got to know what you're doing.
It's easier to see what happens because you like get it.
All right, we'll look at this last example, and then we'll take off.
But it's not that bad.
So the natural log of x dx, we don't see a product there, but that's fine. For integration by parts, we would still say I want u to be the logarithm. Yeah, you can view that as 1. I want u to be the logarithm, and then that means dv has to be dx. So that's really a function though, right? Because that's 1 times dx. So we're just saying let dv be 1 dx. Okay. So that's perfectly acceptable to do. It's still technically a function of x. And the derivative, 1 over x, integral is x. So that's really the main thing to point out in this example. It doesn't necessarily have to be a product. Okay. So the antiderivative of ln of x, we have uv, x ln x, minus the integral of v times du. Notice v times du is just dx. So we have x ln x minus that integral, which is just x. So there you go. That's probably, honestly, an antiderivative worth knowing, just without having to integrate it by parts.
So how would you do that tab?
So, yeah. So that one's, those kinds like that it's kind of tricky with using tabular integration. But here we go. I don't know if this is helpful or not. So we see with this here, if we keep taking its derivative, we keep getting functions of x. It will never diminish.
We just have to recognize that.
So there is, and there are some disadvantages. So if I say, make sure that we change these signs to positive, negative, etc. If I say that's x ln x, then I have this product, right? So that's minus, what would that be? That's x over 2 minus x over 2. But where would we stop, right? Like that just keeps going and keeps going and keeps going. So that's kind of the disadvantage of this. You've got to recognize now here, if I go across, I could write it like this and keep adding stuff to it, or I could say it's x ln of x minus the integral of their product, now that I'm moving horizontally. And their product is -1. And say, well, if I did that, I'd definitely end up stopping. So
it's like sine cosine, or that's,
yeah.
then it's set up sine 1, cosine the other. And once you get back to something where if you did this, the integral's the same as when you started with.
Yeah.
That's what you're saying.
Right. Yep. All right. So yeah. Anyhow, anybody have any questions? Y'all ready to go, right?
It was like X to
So you're talking for the last 10 minutes. All right. Have a great weekend. See ya.